Welcome to our September meeting for Silicon Valley Graph. This is the first meeting of the new year, which for the 2021 year. The Silicon Valley chapter for people in computer graphics. It's a volunteer-run organization. Currently, we have 5 officers. I'm Alex Junkarik. I'm currently the chair. The chapter is entirely a volunteer-run organization. If you'd like to help organize the chapter, please contact us. So tonight we have 4 speakers from Intel Research Labs. We have Ronald Azuma, Alexey, Joshua Ratcliff, and Santiago Alfaro. And so we can now begin our presentation.
All right, thank you. ThinVR, a VR display approach providing a wide field of view in a compact form factor. Presented by Joshua Ratcliff, myself, Alexey, Supikov, and Santiago Alfaro. And we're all, as he said, researchers in Intel Lab. So before I begin, I should note that this is a research project, so we won't be discussing Intel's product roadmap in this presentation. So here's an outline of today's talk. I'll start with some high-level discussion of our approach. Then Santiago will discuss problems around prototyping and device fabrication. Alexey will dive into the details of the design space and optical design, and then I'll come back at the end to speak to limitations in future work. So motivation and approach. Virtual reality head-mounted displays have seen increased adoption in recent years with millions of units sold. However, numerous technical challenges have stymied their broader adoption. One set of challenges that interested us were device compactness and field of view. Despite major advances in display technology since the 1980s, today's commercial systems retain much of their bulkiness, and it's challenging to achieve both an ultra-wide field of view and a compact form factor at the same time. A major reason for this bulkiness is the large optics and concomitantly long focal lengths required. We will discuss this today and examine our own approach to it. There is a rich body of prior work in this area. For the sake of time, I'll focus on 3 areas that we found particularly interesting. First are canted display systems. These HMDs tilt the angle of the display relative to the face to provide a 180-degree field of view. In this respect, they succeeded the task, but still remain bulky due to their large optical elements and tend to suffer from peripheral pupil swim distortion, which is a topic that we'll get into later. Next are a class of optics known as Pancake Optics. These systems obtain impressively compact form factors by folding the optical path. In reality, this folding is usually a process of bouncing light between layers of lenses facilitated by polarization. However, there are issues. It can be difficult to achieve an ultra-wide field of view and a compact design at the same time. Furthermore, there can be substantial headaches with transmission efficiency, ghosting, and cost. Michael Abrash spoke at a recent Oculus Connect about this, which I'd recommend anyone interested to watch. Finally, we have near-eye lens array-based displays. Rather than using a large monolithic element, in this case, the optical system is an array of lenslets. Lemon and Lukey demonstrated light field output in a near-eye lens array system. This presented the user with accommodation cues and retinal blur, 2 features which add visual comfort and realism. However, this came with a fairly extreme loss of spatial resolution. Furthermore, an ultra-wide field of view wasn't demonstrated and could be challenging with the homogeneous arrays that were used. A picture of one of these prototypes is shown in the lower right. Note how exceptionally thin this display system is. We were very impressed with this aspect of their approach, and were inspired to devise an approach of our own for near-eye lens array displays that achieves a 180-degree field of view in a compact form factor. Furthermore, we seek a more moderated spatial resolution trade-off by specifically not supporting retinal light field output. Okay, so how would this work? Well, in a conventional VR HMD, a large lens is placed in front of a display at a distance slightly less than the focal length. This creates a virtual image, usually 1 to 3 meters away. A wide field of view requires a larger lens. Unfortunately, for performance reasons, larger lenses require longer focal lengths. Thus, VR headsets derive much of the bulk from the empty space between the optics and the display. It turns out that lens arrays may be of some help here. By scaling the lenses down and using an array of them, the focal lengths remain small. Each lens maps to its own region on the display, known as an elemental image. In turn, each of these elemental images contain a subset of the original image, shown as a rainbow on the far left. Note that there is some overlap between image regions. This is a necessity for creating what's known as an eyebox, or a region in which the eye can move relative to the display and still see a coherent image. This has implications for optical and geometric prototype design, which we'll discuss the mathematics of in detail later. Finally, when all regions of the display are seen through their respective lenses, a comparable image is formed in the eye. So in our approach, we combine a curved heterogeneous lens array with a curved display for each eye, offering a wide stereo field of view. A cylindrically shaped array simplifies design complexity by reducing the number of unique optical elements. We create a single column of lenses and then replicate this column of lenses along a cylinder. In fact, due to the column symmetry, only a half column of lenses actually required custom design. Nevertheless, even this presented us with a challenge. So as for contributions, we claimed 4 areas that we hope to provide the research community with some insight. First, we provide a design space analysis of curved lens arrays. Second, we created an optical design that achieved sufficient spot size and pupil swim performance, which was a non-trivial task. Third, we made the design a reality and demonstrated it with real-time and high-resolution implementations. And then finally, we provide some assessment of what we built. So you're probably wondering, did it work? Well, this video shows what the user actually sees as the eye moves into the eyebox. Forgive the frame rate here over Zoom. We shot this using a wide-angle camera with an aperture set similar to the human eye. You can see that as we enter the eyebox, the image fuses nicely. So how do we render the underlying image? Well, we start with an input image of a cylindrical panorama for each eye. We then create a lookup table to map this panorama into elemental images on the curved display. This is based on our optics ray tracing data, so that the resultant integral image compensates for optical distortions. For real-time implementations, we use the Google Daydream API to access low persistence display mode and then head orientation data. These images are rendered at 60 frames a second on a Galaxy S9 phone. The photos on the bottom show an observed scene and the integral image that's used to create it. Next, Santiago will discuss prototype fabrication.
Okay, so hello. So for this project, we developed 2 prototypes. And as you can see here, one was an static prototype and the second one was a dynamics prototype. The static prototype was using a film and the dynamic was using a couple of cell phone screens. And we'll get into why we went both ways. Each prototype has its own advantages. So in general, first we have to design the whole thing. So the first thing we need to do is there's constraints around the lenses that we need, and there's also constraints around making something for the human face. So one of the most critical things that we needed to look into was the interpupillary distance, which is the distance between your pupils. This is going to be a device that is going to be so close to your face that you need to match each individual's IPD. And in addition to that, there's things, of course, like head size, nose size. We're going to have to I was going to have to make something that was going to be dynamic enough that everybody would be able to use it. And then things that I couldn't move, that I had to work with was things like the screen size. We were going to use a cell phone screen, the focal length that the manufactured lenses were going to deal with. So all of these things we're going to have to be taken into account for our final designs. So on to manufacturing the lenses. So a traditional way of manufacturing lenses is injection molding, but for a research project where you only need 1 or 2 lenses, that doesn't make economic sense. Molds are too expensive and they take too long. So we went with rapid prototyping, and with rapid prototyping, there's always some caveats. You can do, so we tried 3D printing in a clear plastic. We ended up going with a CNC machine that would diamond cut the lenses directly on acrylic. Now, the problem with this, as you can see in the bottom image, is that even if in the computer, when we design the lenses, the joint between 2 lenses is going to be perfectly infinitesimally small, but in the real world, it depends on the size of the diamond and the size of the bit that's cutting it. And we'll see later, this contributes to most of the artifacts that you see in the final images. So once I have the basic design and I have back the lenses that we manufactured, here's another problem that happens between the real world and the computer simulation, is that once you have the manufactured lenses and the manufactured parts, none of that is going to match exactly what you had in simulation. So the focal length is not going to be exactly the same. The alignment of the lenses is not going to be perfect as we wanted in the simulation. So my device and my prototype needed to have every single knob necessary to be able to locate the lens at the right location to the screen, and both of these inside the rig, both of these in front of your IPD, and everything had to change and had to be adjusted. This is what contributes to the large size of the prototype that you see here. But as I get to know what the different qualities of the manufactured parts, then everything starts to go back down and become more compact, which is one of our objectives. So the other thing that was a problem with the static display, because we were using a printed film, is that I needed a backlight, and we couldn't get a curved backlight. So there were two approaches that I used for this. One was taking a clear acrylic cylinder and cutting it and etching it on the laser cutter so that I could use an LED array so that I could light it from the side and have the light propagate inside the acrylic and come out through the edge. This was a good approach, but it was very hard to get an even illumination all across the backlight. So then the other thing I did was we used an electroluminescent panel, which is easy. You can just hook it up to your power source and you can cut it whatever shape you want. And that is, from the get-go, it's a very even light, but it's not very bright. So in the end, for our final prototype, we went with the electroluminescent panel because I can live with the low light and be smart about what kind of imagery I was going to show in there. Okay. So then here, what you can see here is the static prototypes. In the top, you see the static prototype with the cables for the electroluminescent panel. And in the bottom, you see what you see through the device taken with a DSLR. So this is the static. This is the film that we printed. This is the main reason we used the static, is that we were able to use a 2032 PPI film, which is a crazy resolution, but it's good for us to show the future of how these displays would behave if we had that sort of resolution. And it's also good for us to actually be very careful and knowing exactly where things are not matching with each other. But as you can see, it's a very, very nice image that you get from a printed film like this. So here we wanted to address another thing, is that this is the compactness. So we're offering 180-degree field of view. So in order to compare, we took the device that was offering 180 degrees on the market, and we decided to go with the Pimax 5K, and we wanted to compare the volume. So in order to make a fair comparison, I took the Pimax and I stripped it out of all of its outer casing, all of its bells and whistles, and I just stripped it down to basically the screen and the lens, only the optical elements. I did the same with my device, and then doing after modeling in CAD and having my model in CAD and comparing the volume, it turns out that our device actually gives us around a 50% gain in size. So now onto the dynamic prototype. And as I mentioned, we had to use a cell phone screen. And the reason we had to use a cell phone screen is because we know that they had flexible OLED screens in there. Now, the only problem is how to get the screen out of there. Like, we can take the screen, but the screen is still attached to the glass. Getting the screen out to detach from the glass and not damage the screen was a very complicated procedure. With earlier phones, I could do it myself with dry ice, but then with phones like the Galaxy S9, we actually had to go to a third party and go to very specific machines that would probably use liquid nitrogen to be able to do this. So we got them back, and we have in our hands what would be a 570 ppi screen that we could bend to our will. So here it is, the screen. This is one of the first test rigs. And you can see how the screen is being held in the curve at the right distance from the lens. What you can also see here is the other effect of using the cell phone screen is that there is no other way to drive it or to power it except with the cell phone itself. So from here on, we realized that any prototype that we designed, or any test rig that we designed, was going to have to take into account that the cell phone had to be attached to the screen. So as you can see, the final dynamic prototype, you can see on the left, this is the prototype that you can actually pick up and put on your face. But as you can see, the cell phone is hanging in, behind it. Of course, this is unnecessarily big. Once we had our own screens, if we were to make this ourselves, then we wouldn't have to deal with a cell phone like that. But on the right, you see the actual benefit of having the dynamic screen. The resolution is a little less than the static device, but we actually are able to have animated imagery in there, and we were able to also use the accelerometers and gyroscopes to be able to create a more immersive VR experience where the device responds to your head movement. And now let me introduce Alexey with design space and optics.
Hello, I'd like to give more insight into ThinVR configuration and optics. Fascinated by compactness of near-eye light field display by Landman and Lübke, we wanted to use the same approach to emulate regular stereo HMD. It requires to solve several problems. Maximize possible resolution, make HMD work at large FOVs, and make it easy to fabricate and calibrate. To be useful, the system had to be on par with then modern commodity HMDs. So it should have comfortable eyebox, accommodating eyeball rotations. It should have anatomical but efficient eye relief that was about 22 millimeters, spatial resolution of 9 pixels per degree, assuming 810 ppi displays. The device should be thin, so display lens spacing is limited to 10 to maybe 11 millimeters. Those parameters gives a starting point in design space exploration. To facilitate easy fabrication and calibration, we preferred single lens array rather than double lens array. To address large FOV, we opted for vertically heterogeneous lens array and curved it horizontally together with the display surface. The simplest curve geometry, the simplest curve geometry is cylindrical centered at eyeball center. It also minimizes the number of different lenslets we need to design. Regular VR displays use flat geometry, so they use flat display and they assume flat virtual surface far behind the lens. Virtual surface in our system is cylindrical and also concentric with the eyeball. We found that under such assumptions, the eyebox and resolution depend on just two parameters: angular width of lenslets, representing lens pitch, and nominal focal length, which also gives an upper boundary of the device thickness. Next slide, please. I'll talk about some key ideas behind the characterization. In vertical direction, because it's cylinder, our system behaves similar to near-eye light field display by Landman and Lübke, and we can use their math to get eyebox, to get spatial resolution, and all other parameters. So let me step back a little bit to explain the eyebox and resolution. So conceptually, each lenslet is a hole in space. Through that hole, we see a portion of magnified elemental image far behind the lens. We don't show that magnified image here on the slide for the sake of space. When eye moves, different portions of this magnified version of elemental image become visible. So it's pretty much like looking at the far but large billboard through the small hole in the fence. The elemental images share the same pixel colors where their magnified versions overlap, and that creates one continuous 2D image. We call it image fusion, and it shouldn't be confused with the stereo fusion. So we are looking through this hole at this billboard, but if our eye moves too far up and down or left, right, we will start seeing neighboring elemental image, neighboring billboard. So that restricts the range of lateral eye motion. This region for the given eye distance, eye relief, is called eyebox. Actually, its size changes when the eye moves forward or backward, sweeping a 3D volume. This 3D volume is called viewing zone. And in real life, the shape of this viewing zone also depends on distortion. So it could be curved and not necessarily be a segment of the pyramid. The resolution is defined by the total number of pixels visible through all lenses at a given eye position. Next slide, please. The horizontal dimension is curved, so how we derive eyebox and resolution. So we started with piecewise linear approximation, which is optically feasible but requires unrealistic faceted display. Then we modify it to work on curved display surfaces. We take thin lenses of nominal focal length f placed on cylindrical surface. We assume that elemental images are flat segments of the cylinder, and their correspondent virtual images are also flat segments of the virtual cylinder. Such simplified system enables very easy analysis. The viewing zone for each pair of lens and elemental image is easy to compute, and then rotating this viewing zone continuously gives us a conservative estimate of horizontal eyebox. The resolution is again number of pixels visible through all lenses. Then we curve the elemental images, keeping them on the same cylinder. And we curve their virtual images to conform to the virtual cylinder surface, which doesn't change from the piecewise linear case. The eyebox stays the same. The resolution needs to be corrected to account for uniform pixel pitch on this virtual cylinder. Next slide, please. After putting it all together and doing some algebra, we observe the following. Spatial resolution increases with the nominal focal length, but makes system bulkier or reduces the eyebox. Making lenses too large puts us at risk of poor optical performance. Next slide, please. The eyebox gets larger when this billboard, the virtual image of elemental image gets larger. This happens when focal lengths become smaller, magnifying the elemental image more, or when the elemental image itself becomes bigger. The angular lens pitch in the horizontal direction defines maximum horizontal elemental image size. So elemental image can't increase independently from the angular lens pitch. Next slide, please. By choosing cylindrical geometry, we made our life easier in terms of characterization, but there are still substantial issues. First, since vertical direction is not curved, we cannot use this trick using very nice lenses. We need to do something to address large vertical FOV. So, because it requires good off-axis performance from the lenses. Our attempts to use the same lens in vertical direction failed miserably. You can see the results. They are kind of rotated horizontally on the left side of this slide. So we decided to design heterogeneous lens array. The second problem, which you could see on the video, is a view-dependent distortion called pupil swing. This aberration is present in all HMDs, and human eye tends to forgive it. But in case of lens arrays, lenses are smaller, and we need to bring all these images in fusion. The pupil swim can actually break the fusion if left unattended. Next slide, please. So now we know where lenses should be, what they must do. They have to image screen cylinder to the virtual cylinder within our ideal viewing zone. So it must be trivial to set up a lens design tool and get a solution. To our surprise, standard optical design tools aren't suited well for our problem. In addition, if we use such tools, it takes about 2 weeks to run optimization every time configuration changes. Aiming at faster design iterations, we decided to make our own lens array design and simulation tool. It is based on very fast and scalable ray tracing library made here at Intel. It's called Embry. Then armed with real-time ray tracing, we could finally see what a person would see looking through the optics. So we could model and simulate not only a single lens, but the entire lens array. We used very simple eye model. It's just a camera with flat sensor and thin lens having 4 to 8 millimeter aperture. Importantly though, we were able to observe how image changes when optics is modified by manual cranking of polynomial coefficients. Or we could visually track the optimization progress and abort it very early if we didn't like what we see. It is worth to note that our software is not intended to replace professional optic design tools because it was made for only one purpose: visually assisted interactive design of heterogeneous lens arrays for VR. And every word in this phrase is important. Next slide, please. The design problem itself is cast as finding a lens performing ideal imaging of display points as virtual image points using geometry-based cost function. It's additionally constrained to make lens array feasible to construct. So lenses shouldn't be very thick or very thin on the boundaries, or they should not overhang like that. The lenslet is defined by two free-form surfaces based on Chebyshev polynomials. To make ray tracing fast, we pretessellate the surfaces using fine regular grid in X and Y. The grid is fixed throughout the entire runtime. The BVH acceleration structure for ray tracing is built just once and then refitted every time polynomials coefficients change. That way, we can afford very fine tessellation, hence very good precision, maintaining real-time ray tracing performance. Next slide, please. Again, we lose a lot of important functionality of standard lens design tools, but we are able to try a design in a matter of minutes to hours instead of weeks. For actual fabrication, we selected a geometry with a repeating column of 5 lenslets. That required us to design only 3 different lenslets. For each lens, we started with a thick lens model of a given focal length. We focused our virtual eye at virtual image distance. And then, using real-time ray tracing, we visually found good conic coefficients. Then, interactive optimization fine-tunes the lens using polynomial coefficients. Next slide, please. When we got this newly designed heterogeneous lens arrays, we immediately saw improved image quality and fusion, as you can see on this slide. Next slide, please. The fabricated lens array behaves similar to simulation. Next slide, please. We imported lenslet geometry into Zmax for MTF measurement, and it showed noticeable improvement of optical performance of heterogeneous lens array. Next slide, please. The static prototype that uses 80 pixels per millimeter light well printed films showed us that image quality improves with underlying display pixel density. This is an image captured from it using wide-angle lens. We were so happy with the results that we wanted to show both static and dynamic prototypes live at emerging technology at SIGGRAPH this year. The demo was accepted, but because SIGGRAPH was virtual, there were only videos and slides instead of the live demo. Next slide, please. We evaluated visual quality of assembled and calibrated physical prototypes. Although pretty good, the fabricated devices exhibit visible artifacts along lens boundaries and some residual pupil swing. There are multiple reasons to it. First, rapid prototyping methods trade low cost and short lead time for some precision, so there is a visible error in lens geometry. Second, lens boundaries were optimized for mechanical feasibility, but we never thought we had to do something for optical performance. And the third, the lens array is not AR-coated, so there is a stray light. Nevertheless, the resolution numbers for the static prototype prototype print version are pretty good. The resolution of dynamic version with flexible OLED screen is also in the ballpark of what we wanted to achieve. We got 6 ppd here instead of 9 because we used lower PPI display than we originally planned. Next slide, please. I want to remind that like any near-eye light field display, we trade some part of display pixels for the eyebox. We wanted to see how this 3D viewing zone volume looks like and how it compares with our conservative cylindrical estimate. And having ability to dump all the rays, we estimated a slice of pyramid fitting inside the actual curved viewing zone of each lens. Then we took an intersection of all zones and it gave us real geometry of the eyebox. And as you can see, it has nothing to do with the box at all. Even the cross section of it is not a rectangle. Next slide, please. Moving the camera on translation stage, we were able to verify that real system has the eyebox at intended pupil locations. And finally, let's look at FOV numbers. Our final design provides about 130-degree horizontal FOV per eye with stereo overlap, which is limited by presence of the nose on a typical human face and rectangular display shape. The vertical FOV is about 81 degrees. Thank you for your attention. Now I'm handing it over to Josh again.
Thanks, Alexey. So yeah, I'll go ahead and speak here to limitations and future work. So what are the limitations of our work and how might we address them? Well, first, you probably noticed we couldn't find flexible OLEDs with the driver board. So this led to prototypes that were frustratingly bulkier than necessary. Also, as with many HMDs, the underlying aspect ratio is suboptimal. Second, our eyebox is a little smaller than traditional VR displays, so mechanical IPD adjustment was crucial. Third, with the curved shape and form-fitting dimensions, the design doesn't accommodate eyeglasses very well. One solution may be the use of curved Alvarez lens inserts. Alvarez lenses are lenses whose elements can slide along each other to change the focal length. Perhaps more important is to note that the resolution in our approach is still substantially lower than traditional designs, by about 65% in this particular example. Eye tracking could improve this if we were to redesign the optics, pair it with an eye tracking system, shrink the eyebox down, and then try to trade back in favor of resolution. Finally, a cylindrical design was chosen for its prototyping simplicity, not for industrial design purposes. A fully ergonomic design would require custom designing numerous lenslets, but we think this would be a worthwhile task to achieve further gains in device compactness. So to conclude, we believe this is the first work to demonstrate and analyze the promise of using curved heterogeneous microlens arrays in VR. We've demonstrated a 180-degree field of view, a compact form factor, optical performance that's acceptable both in terms of off-axis imaging and pupil swim, and we also provided a design space analysis. We hope this work stimulates new approaches and accelerates the day when VR becomes ubiquitous. For more details, check out our paper from IEEE VR. Thank you.
Okay, I think we have time for some questions. So if anyone has questions, can you please type your questions in the chat and I will then read them. Well, there's one question here that asked if the slides will be shared somewhere.
I think you're recording the video, right? And putting it on YouTube?
Mm-hmm.
Okay, so I think we're sharing the materials that way.
Okay. So are there any more questions?
And if you Google search on ThinVR, you can find the paper, and there's also other recorded videos, such as the presentation that Josh gave at IEEE VR. So there's already a fair amount of materials already out there.
Someone wrote, how does this compare with FBs? I'm not sure what that means. Facebook's maybe?
Yeah, I think he's referring to a research paper actually from SIGGRAPH from Facebook.
Right.
So their implementation, they had done a holographic implementation of a pancake optical system. And that was in order to achieve basically the thinnest possible prototype they could make. It's a very interesting approach. Of course, we talked a little bit about pancake optics at the beginning of the presentation. So with an implementation like that, you're buying a bit of the problems with both pancake optics and with holograms. But overall, I'd say it's a really interesting approach. For them, though, they're focused on the thinness, but not necessarily the field of view. For us, we wanted to achieve that full 180-degree field of view and then drive thinness with the use of a lens array.
Right, and I would say there's different pros and cons. Obviously, the Andrew Maimoni's work and I think it was Maimoni and Wang, work at SIGGRAPH is very, very impressive. You have different trade-offs. So, for example, in theirs, they don't have the spatial resolution trade-off that you do with when you're doing lenslets. On the other hand, when you use lenslets like we do, you can actually use a traditional display, like an OLED display, which people have spent billions of dollars to make really nice, high-quality images on there. And in comparison, when you're trying to illuminate something with lasers and go through HOEs, holographic optical elements, you usually have compromises on the image quality. So it's different pros and cons. I think we need to pursue, as a field, I think we need to pursue novel types of approaches like ours and what Facebook has been doing to try to get much more compact and wide field of view virtual reality displays. It's not going to happen unless people try different types of configurations like this.
Okay. Someone also asked, would the lenses have to be adjusted for each user?
No, we actually designed our lens array in a way that as far as your eye in this viewing zone that we showed in the end of my part, any eye could see fused image. That was the key point of the design.
You would have to adjust IPD but not the lens per se.
Yeah, you need to bring both eyes in those viewing zones.
And also, as Josh pointed out in the limitations, this does not perform prescription correction. And it's too compact to actually put your own glasses underneath. So that is a step for future work.
Okay, so I'm gonna ask, what type of test pattern would you use to tell user if in the optical position of their eyes? So I think, I'm not sure if does that make sense, or maybe Carl can.
I would say any high contrast kind of maybe pattern with continuous lines through the entire FOV would be sufficient.
Yes, but then also in the test that we've done it and when we put it on people, what we do is we measure the distance between the pupil, and we decided in such a way that the eyebox is big enough that once you put it on, you're pretty much inside the eyebox, and then you'll see a coherent image. If the image is not coherent, you would immediately notice.
So generally speaking, if your IPD is matching correctly in the horizontal, you'll probably be where you need to be in the eyebox. Vertical might require some extra patterns, though, just to be sure that you're centered. So when you look up and down, that you're making the best use of the eyebox and you're not too far down to the top or the bottom in the central position.
Okay, there's also a question that says, regarding resolution and FOV at the periphery, low resolution is acceptable. Can you take advantage of this to increase the resolution closer to the center of projection to yet get wider field of view? How does this affect the shape of the display and lenslets?
Well, the eyes would still rotate, right? So you will have to maintain good resolution through the supporting eye rotation. We could benefit from foveated rendering, and we probably would do some additional corrections, but it requires so low latency system that it pretty much requires redoing the entire stack, starting from camera, USB interfaces or whatever camera interfaces you have, rewriting all the drivers, changing operating systems. So pretty much you have to come up with the entire platform to really support eye tracking really well.
Yes, but that's the rendering workload. I mean, I think the question was also about FOV displays itself, right? Could we actually change the resolution depending upon where the eye was looking? Interesting idea that what we currently have is not a foveated display.
Is there any more questions?
There was a comment about our determination to separate out the screen. Yes, thank you. We were very determined.
I would say that Samsung made a lot of money off of
We needed that
destroyed
screen.
A lot of cell phones.
Yeah, the Samsung doesn't make it easy to liberate the screen from the glass.
And it gets harder as you go in the generations. Initially, we were doing the Galaxy S6.
The S6.
Then we moved up to the S9, and it was way harder.
Yeah.
So you can't buy just the screen. There's no way to buy just the screen itself without buying the whole phone.
You can buy just the screen, but it will always come with the glass attached. And that's the problem. Like they don't conceive of a reason why you would want the screen without glass.
Oh, I understand. Okay.
Yeah.
Just how long does someone asked? How long did the prototype take to build?
Oh, gee, it would be hard to give an exact estimate for that because it was such an iterative process. I mean, we were going back and forth with Lens Designs for a long time on this.
Yeah, I mean, the project has been what? Year?
Yeah,
Yeah,
no, it's been a while. I don't know how to really define that because, as Josh said, it's been many iterations. But
so
what
I would say, go ahead.
No, I just am very proud of the team for their determination and staying with it despite and saying that we had to achieve certain milestones, such as actually being able to see the display in a sufficient eyebox and having pupil swim distortion under sufficient control that you actually got image fusion. I mean, those we kept going and going and going until actually achieving that.
So I would say if you know what you want to build, you can do it quickly if you have a team of talented people.
Thank you.
Someone asks, are there any future plans to create a better design or manufacture it?
Well, we're not talking about specific future plans or what Intel's thing. We are talking about the research project that we've done up to this point.
Mm-hmm.
Someone asked, did you ever consider hexagonal lenslets?
I mean, it was something I think we briefly talked about, but we didn't seriously pursue that. Anything to add, Alexey?
I think we wanted to solve the regular grid type of arrangements first, and once we know how to do that, we could do hexagonal. Although I don't see a lot of benefits from that.
Right. I mean, now you're dealing with 6 lenslet boundaries rather than 4.
Right. Correct.
So someone asked, what material are the lenses made out of?
These are made out of PMMA. So the prototypes that you see here, they were machined, I think, on a 5-axis CNC mill directly in PMMA.
Yep.
So it's just one material, one refractive index.
Okay.
So to speak.
So Philip, are these plastic then?
That's correct. Yeah, that's a type of plastic.
Okay. Someone asked, could triangular lenses be good?
Well, I don't know. I have to think about that. I mean, you got to think about the underlying usage of the displays. You break it up into elemental images. But I'm not sure whether that would be very efficient or not. I haven't even thought about it, honestly.
Yeah, I think those questions of hexagonal or triangular, as far as the fabrication goes, I don't think it would matter to me, but it's more about like having to deal with a lookup table that has hexagonal as a base instead of like a straight up grid and stuff like that.
And also, how do you define the viewing zone for this triangular shaped lens? It would have a lot of narrow regions, right? The one good thing about having the rectangular lenses, square lenses, or rectangular, you'll have the ideal viewing zone is a slice of a pyramid, expanding when the eye moves away from the lens. You're losing this property, and your viewing zone is actually intersection of all those viewing zones. So I don't think that triangular in particular is a very good idea.
Someone asked, would a larger screen or display be better? Is there an optimal size?
I would actually say a higher resolution display. Actually, if you look at the pictures of our prototype, the displays were honestly too large. We didn't need all the size that they had. We just needed more pixels on the displays. So smaller, honestly, for our purposes, at least for this particular prototype. But it's a large design space. Maybe you come up with something different.
Yeah, I suppose you can get somewhat larger field of view, but then it makes the manufacturing problem harder, right? I mean, if the display is too large and things, you know, get too close, I mean, you know, there has to be room for the nose, etc.
How
that's
were you able to integrate this hardware with Unity along? So, how were you able to integrate this hardware with Unity along with the lens distortions?
Oh, that was relatively straightforward. We were able, because we can ray trace through the lenses, we can build lookup tables, and then we render cylindrical panoramas, and we can map those cylindrical panoramas with the lookup tables as just indirect texture search. That's it.
Okay, so another question is, what would you want the lenslet boundaries more? Would you want the lenslet boundaries more mismatched between the eyes, so the eye might select the lens, the less distorted image, or would fusion be a problem?
I can't picture that question.
Not sure I understood the question, sorry.
I think if I properly understand the question is, you have those lens boundary, right? Is it important where the lens boundary is located with respect to kind of the central viewing direction of one of the eyes? So if I look straight into the lens boundary, it might produce worse image than when in the case where I looks through the lens.
Yeah, okay.
I think it's something like that.
Currently, the answer is yes, because of artifacts. If everything was perfect, then the answer would be no, I think.
Yeah, because lenses are closed, and if we assume that lens boundaries are very, very thin, they're just defocused. Your eye is focused mirror or more away on the virtual surface.
Phone screens are made for looking at 1 to 2 feet away, not optical for 1 inch away, right?
Well, first I'd point out that phone screens are pretty much the basis of all the modern VR headsets that we have. I mean, it's really a question of being able to focus on the pixels themselves with your optics, and are the density of pixels on the display high enough? And in that sense, yeah, iPhone screens are suboptimal because they don't really need the sort of resolution that we would like to have in virtual reality. That's been making some improvements, but honestly, it could go a lot further.
I guess it's getting close to the hour, so if let's wait for a minute and see if we get any more questions, and then we'll call the meeting to an end. Give one last chance for one last question. Okay, I don't see any more questions, so. Oh, oops.
Something about a lot of hard work.
Okay, I guess someone asked if this will be brought into production, and I think you've already answered that, Arlita.
Yeah, we can't comment on Intel's product roadmaps at all.
Okay. All right, I think we're getting close to the hour, so let's call this meeting to an end. I want to
actually, Alesh.
Yeah.
Could I ask a question? Where people are from here?
Sure.
We have a little poll here. If I can get my cursor over there. So just to see how many are local versus elsewhere. If you'd like to answer that.
Oh.
I don't see the poll.
I see the poll.
People are answering them.
Oh,
No.
okay.
I do see the poll.
Does anyone else see it, or do I just see the results?
I can see the results. I don't see the poll, but maybe nobody asked me.
Yeah, I don't see the button to vote.
I don't see.
I think hosts don't
Maybe
get to vote.
because you're a co-host, you don't get to
Oh.
see the.
Well, that's plus 4 people for Silicon Valley.
I don't know. Someone ended the poll there, I guess. All right.
Silicon Valley for the win.
Okay, so if there's nothing
Thank you.
else, I'd like to thank all the speakers for exciting presentation, and let's hopefully like if you do more work, you can come again sometimes. Thank you all.
Well, please. Thank you.
Thank you.
Thank you all.
Thank you.